C2 common integrals. Let's review some of the common integrals. So let's write down y as a function of x, and then common integral, we just integrate to get the result. If we have x to the n, we would have x to the n plus 1 over n plus 1. See, we're kind of doing the opposite. And we have to add a constant because we went back the other way and took the derivative here. We would bring the n plus 1 down. That would cancel this. So we would subtract 1 in the exponent and get that. And the derivative of a constant is 0. Remember, we talked about you have a function that, say, is something like this, and then here you want the slope and say, the slope here is a constant, so you have this. So if you want to go from the slope to the function, this could have a different elevation, has the same slope. So that's what this plus c is. That's constant that you set depending on your situation. So if you have the cosine of x, then you want here, the integral is the sine of x. We're just doing the antiderivative, compared to what we did earlier. In our earlier class, we had the derivatives, but then if we start with these and go backwards, we're doing the antiderivatives. And that's where we're making a list here. So if you have the sine of x, the antiderivative or the integral would be the negative cosine x plus a constant. And then e to the x would be e to the x plus a constant. And then 1 over x would be the natural log of x plus a constant. Now let's look at some standard tricks. Integration by substitution. Substitution. Say, in this case, we want to integrate from 0 to pi over 2. X times the cosine squared. No, let's see. No, let's do the cosine of x squared like this. That looks a little scary. We don't have that one up here. Dx. Now, when you do integrals, it's an art. You try things, you guess. And when I first studied calculus, integral calculus, that kind of bothered me because it's more artistic in a way, and I like to have a definite way to do things. Well, that's not the case with integral calculus. We have to deal with this situation. So substitution, you try things, see if it works. Like let's let u equal x squared. Then what you do here is you take the du, because we have to have a differential here. So du would be 2x dx, which you can think of that if you took the derivative of du dx, you get 2x. So in differential form, we could write du equals 2x dx. Now, when the x here, is going to go from 0 to pi over 2, what does the u do? Well, it's squared, x squared. So what the u does is the u is going to go from 0 to pi squared over 4. We're going to do a change of variable here, see, with this substitution. So calling this the integral I, then the integral, all right, so the integral here, let's go ahead and review stuff. This is 0 to pi over 2. This is the integral we're starting with. X cosine of x squared dx. And now using the substitutions, before I do that, let me fix this so I can make this substitution. I really want to have a 2x dx here, because that's what I need to make that a du, but I can't put the 2. I have the x, I can put the 2 in, but then I have to put the 1/2 in to cancel that. So I'm going to put down a 1/2, so I can't change the thing. So 1/2 from 0 to pi over 2. I'm going to have the cosine squared x, and I just move the x now with the 2 over to the back. And this is the insight with experience, this kind of a trick. You kind of see that if you had here x squared, you had the differential x dx is going to be related to that u being x squared. So I'm going to show you the details here. I want the 2x dx here. I had the x dx, but I need to put the 2 in front. So I put the 2 and then divide by 2. And then I see that this is going to be a du. And you see now things are melting away. This is cosine of u. All I have to do here is change the limit of integration, because I'm integrating with u now, from 0 to pi squared over 4. And then I have the cosine of u du, very friendly integral. In fact, I know what that's going to be. That's going to be the sine. It's going to give me the sine. And we don't have to worry about a constant, because when we put in for the definite integral, we're going to subtract these two, and the constant would drop out. And if you had the constant and then put the upper value in with a constant and subtract the lower value with the constant, constants go away. So we don't worry about the constant when we have a definite integral. When the integral is indefinite like this, no limits are there, then you got to be careful and put the constant in. So this one here, the integral is then equal to integrating the cosine gets me the sine. So this is going to be 1/2 times the sine of u, and we're going to go from 0 to pi squared over 4, and that's going to be 1/2 of the sine of pi squared over 4, and then minus what it is at the lower limit, which would be the sine of 0, which is 0. So the answer is 1/2 times the sine of pi squared over 4. So, nice result. Now I'd like to do an integral showing a trick. And this is going to be have the title integrating cosine of squared or sine squared of theta over an integral multiple of pi over 2. Now let's look at this. Let's say we have here x, and well, let's do theta since we're using theta up here. Let's make that theta. So here, if we look at the cosine does something like this. Let's go ahead and put some values in. Say 0, pi over 2, pi, and then 3 pi over 2, and then here 2 pi. All right, so a half a pi, a full pi, 1.5, and then 2. So here, the cosine starts out here at 1, and then goes to 0, and then it goes to -1, and then it comes up to 0, and then comes back to repeat the cycle again at 2 pi. Now for the sine, okay, that's the cosine. This is the cosine of theta. Then for the sine, you would start here and go up to 1 when you get to pi over 2. Then you would come back down. Then you would go down here and then come back up like this. Now my point is that if you look at this pi over 2, in multiples of pi over 2, you have this nice area here under the red curve. But if I look at this blue area, it's the same area. See? It's the same area. And then you look over here, you have the same thing going on. You would have a half cycle there and a half there. But when you square them, they're going to be both positive because you don't have to worry about negative area. So the point is the integral is going to be the same when you go over an integral multiple of pi over 2. So that means if I went to integrate, say, from 0 to pi over 2, cosine squared theta d theta, that's going to be the same as integrating from 0 to pi over 2, the sine squared. And that's going to be the same for 0 to pi, or replace 0 to 3 pi over 2, or pi to 3 pi over 2, as long as I'm going a multiple of pi over 2. So that means this integral, or that integral, which looks scary to me, would be 1/2 from 0 to pi over 2 of cosine squared plus sine squared. A half of either of them. A half of them summed up. Now be careful. This does not work if you don't go to the integral multiple of pi over 2. But see, this happens so often in physics. I'm going from 0 to pi, 0 to 2 pi. I can use this trick, and I don't have to worry about trying to solve that more complicated situation. So this is a 1. And then you say, well, wait a minute, that's a 1. This is going to be easy. The integral then is 1/2 from 0 to pi over 2 of just d theta. Well, that's going to be 1/2 theta from 0 to pi over 2. That's going to be 1/2. You put the upper limit in, pi over 2, subtract the lower limit like this, and that's going to be pi over 4. Integral's done. My advisor at St. Joseph's College in Philadelphia taught me that. Dr. Richard Houston showed me that trick one time. Thought that was really cool. Really cool trick. Let's do another thing here. Let's do integration by parts. Now for integration by parts, I like to think of it as the product rule. If you have two functions and you take the derivative like this with respect to x, you take the derivative of the first times the second plus vice versa. So the derivative of the first is du dx. I'll put the v first. So du dx like that. And then I'm going to flip them, then u d v dx. So this is the derivative of the first times the second, and this is the first times the derivative of the second. So writing this in differential form, d u times v like this, is v du plus u dv. All right. Now, never say multiply both sides by dx. Can't do that because these are derivatives. But what you could do is you could make these deltas where delta x is not 0 yet, and then multiply both sides by delta x when it's not 0, and arrive at a reasoning to write this equation down like this. But this is done very often, these two forms. So now what we do is we say we have one of these. Say we have a u dv like this. So you have this one that you're trying to figure out. Well, that would be equal to the left side with an integration minus this part. Now, the reason you want to look at this is that it might be that this integral is too hard to do. But using this trick, this integral may be easy to do. And then this is not an integral at all, because if you integrate a differential, you just get uv. So this one's basically done. So when you switch the u and the v, you pay for a price, you get this, but that's really a freebie, because see, this is going to get you uv, and you're just going to have this like that. And this is done so often with limits, so we don't worry about constants of integration. So I'm going to do an example here. Let's say the integral we want to do is to go from 0 to pi over 2 of x times the cosine of x dx. So the way you apply this is, let's try picking one to be u, and then this other part here is dv. And remember that doing integrals is an art. You pick something to be u, and the rest here dv, and that didn't work, you might flip it and pick the other one, to be the u, and the other one to be the dv, all right? So we're gonna try this first, and if we do this, then I like to make like a little assignment here where I write these out, like say u equal to x, and then dv equals cosine of x dx. So I like to write out like a little group of 4 things here. So here, if I wanted a du, it would just be dx. And then if I wanted here the v, it'd be going backwards, the antiderivative, to get the sign. So if I have dv, I'd have here cosine of x dx. Think of this as like dv dx is the derivative of the sine, is cosine. So I kind of like doing this to have like 4 things. And then I can apply this rule fairly easily. I just take for this one, I'm going to look at these two together. And then for the v du, I'm going to be looking at, these two together for this second part. So this chart helps me figure things out. So that means the integral would be, the first thing is I have u times v. Well, what is u? It's x. See my chart, just pull it right off. This is x times the sine of x. See how easy that is when you have this little group of 4 things. And then we're going to go from 0 to pi over 2. And now we need the minus sign. And now we're going to have the v du. So that means we're going to have the sine of x. And then the du is the dx. We put the dx there, and we're going from 0 to pi over 2. And see, this integral is not easy to do. And this one came as a bonus. There was nothing to do there. So therefore, the integration here, you put in the upper limit. This would be pi over 2 times the sine of pi over 2. This one here. And then you would subtract x being 0 times the sine of 0. Well, this is 0 times 0. Didn't even have to worry about that. That's going to be 0. And the sine of pi over 2 is 1. So this is 0. So that takes care of this one. Well, what about this one over here? Well, you'd have a minus sign, and then if you integrate the sine of x, you get minus the cosine of x. You may want to kind of remember these, because these are real basic ones. And that's going to go from 0 to pi over 2. And here, the minus signs will cancel, so I'll have the cosine of x 0 to pi over 2. And this is going to be the cosine of pi over 2 minus the cosine of 0. Now the cosine of pi over 2 is 0. The cosine of 0 is 1, but then there's a minus sign floating around, so you want to have that minus sign there. So that means the integral is, the first part here is pi over 2, then the second part is minus 1. So that's a nice little example of doing an integral with integration by parts. And I don't memorize this formula. You can, but I just start with this because I love the product rule. I'm in love with the product rule. So if I can use the product rule to do something, I just set it up and then I'll do the subtraction and have the result here. So this is just so easy to write down. Once when you write that down, so you have this, and then you can pick one of these, and then it would be equal to the one on the other side, and then minus the other one. All right, that's it for now. See you in the next class.